Welcome to our today's lesson, and today we are going to plot the B.M.D as well as the S.F.D for an overhanging beam that is loaded with the UDL between the span A all the way to B, and on the overhanging end D, the beam is loaded with a point rod of 10 kilonewtons. And ladies and gentlemen, please, we are requesting that you subscribe to our channel, and you are going to receive or to be notified every time we record and upload a new video. So welcome to our today's lesson. Now we are going to begin with bending moments calculations due to vertical loads. And in this case, when we talk about the vertical loads, between the span A and B, we have a UDL of 6 kilonewtons per meter. Between span B and C, we have a UDL of 10 kilonewtons per meter. And we are going to begin with the span AB. And for the span AB, we are going to calculate the maximum bending moment, which will be given by W1 L1 squared all over 8. And this is going to be equal to W1 is the UDL of 6 kilonewtons per meter. So we have 6. L1 is the span AB, which is 4 meters. Therefore, that is 4 squared. We divide that by 8. And this is going to give us a maximum bending moment of 12 kilonewtons meter. From there, we are going to go to the span BC. Therefore, for the span BC, the maximum bending moment will be given by W2 L2 squared all over 8. And this is going to be equal to W2 is a UDL of 10 kilonewtons per meter. L2 is the span BC, which is 6 meters. Therefore, 6 squared. Then we divide this by 8. And when we do so, we are going to get a maximum bending moment of 45 kilonewtons meter. Then we go to the span C to D. So for the span CD, the bending moment at C, that is MC, will be given by the load, the point load 10 kilonewtons times the distance from D to C. So in this case, we are going to have, since this end is overhanging, the bending moment is going to be negative. So we are going to have negative 10 kilonewtons multiplied by the span DC, which in this case is 2 meters. And that is going to give us a bending moment of negative 20 kilonewtons meter. Then finally, the bending moment at D, that is going to be 0. So we now have all the bending moments. So the next thing we are going to do is to plot the bending moment diagram due to the vertical loads. And we are going to begin with the span AB. So for the span AB, we have 12 kilonewton meter. So 12 kilonewton meter is that at that point. So that's going to be a smooth curve, since when we have a UDL, the bending moment diagram is usually a smooth curve. Then for the span BC, we have a maximum bending moment of 45. So let's have it at that point. It is also going to be a smooth curve, since the span is loaded with a uniformly distributed load. So that is going to be a very smooth curve with a maximum bending moment of 45 kilonewtons meter. Then we have the bending moment at C, which is a negative 20 kilonewton meter. So if I approximate 20 to be at that point, the bending moment at D is 0. So we are going to join this bending moment of 20 kilonewtons meter to the 0 bending moment at D, and that is how it's going to look like. So this is a negative bending moment of 20 kilonewton meter. Good. From there, we are going to determine the area of this smooth curve as well as this one between span AB and BC respectively. So we begin with the span AB. Therefore, for span AB, A1, that is the area of this smooth curve, will be given by 2/3 multiplied by its base, that is the distance AB, which in this case is 4 meters. So multiplied by 4 meters times its perpendicular height, which is 12 units. So we multiply that by 12. And when we do so, we are going to get an area of 32 square meters. 32 square meters. Then we are going to find bar x1. And in this case, bar x1 is the distance from the center of gravity of this bending moment diagram all the way to the end A. So this is what we are calling bar x1. And in this case, bar x1 will be given by half the span A to B. So that is a half of 4 meters, which is 2 meters. Then from there, we go to the span BC. Therefore, for span BC, A2, that is the area of this bending moment diagram, will be given by 2/3 of the base B to C, which is 6 meters. So 2/3 of 6 meters times the perpendicular height, which is 45 units. So we multiply that by 45. And when we do so, we are going to have an area of 180 square meters. So we got 180 square meters. Then from there, we are going to determine bar x2. So bar x2 for this bending moment diagram will be the distance from the center of gravity of this bending moment diagram all the way to the end C. So that is what we are calling bar x2. And bar x2 in this case is going to be a half of the base BC, or the span BC, which is 6 meters, and that is going to give us 3 meters. So ladies and gentlemen, that is for the span B to C. Now that we have that, the next thing we are going to do, we are going to apply the 3-moment theorem, or the CLAPEYRON'S equation of 3-moment. So we go to the application of the CLAPEYRON'S equation of 3-moment. Good. So application of the 3-moment theorem, and we are going to begin with the spans AB as well as BC. And the 3-moment equation will be as follows. We are going to have MA multiplied by L1, and L1 is the distance AB. So this is L1, the distance BC, that is L2. So we are going to have MA multiplied by L1 plus 2MB multiplied by L1 plus L2. So we go to 2MB into L1 plus L2. Then we add MC multiplied by L2. So that is MC L2 is equal to 6A1 bar X1 divided by L1 plus 6A2 bar X2 divided by L2. Now, the bending moment at A is going to be 0, since the beam is simply supported at A, and therefore that makes bending moment at A to be 0. So we are going to have the following. Since MA is 0, this part is going to be 0, so we are going to have 0 plus 2MB into L1 4 meters, L2 6 meters plus MCL2, that's going to be 6MC being equal to 6 multiplied by A1, which is 32 square meters, multiplied by bar X1, which is 2 meters. Then we divide this by L1, which is 4 meters, plus 6 times A2, that is 180 square meters, times bar X2, which is 3 meters. Then we divide this by L2, which is 6 meters. So this is going to give us 4 plus 6, that is 10 times 2, 20. So we got 20 MB plus 6 multiplied by, we have the value of bending moment at C, which is negative 20 kilonewtons meter. So 6 multiplied by negative 20. This one will be equal to, this part is going to be to give us so 6 times 32 times 2 divided by 4, that is going to give us 96, plus this 6 and this one will cancel out, so we are going to have 180 times 3, which is 540. Then from there we are going to have 20 MB minus 6 times 20, that is 120, being equal to 96 plus 540, that is going to be 636. Then 20 MB will be equal to 636. We take negative 120 the other side of the equal sign, that is going to be plus 120. So we got plus 120, and that is going to give us MB being equal to 636 plus 120, that is going to be 756. We divide that by 20, and that is going to give us a bending moment at B. Bending moment of 37.8 kilonewton meter. 37.8 kilonewton meter. Therefore, ladies and gentlemen, that is the bending moment at B. And I think we now have all the bending moment values. We can highlight them down here. The bending moment at A, we've said that is 0, since the beam is simply supported at the end A. The bending moment at B, we got it here, which is 37.8 kilonewtons meter. 37.8 kNm. Then we have the bending moment at C, which is negative 20 kilonewtons meter. And then finally we got the bending moment at D, which is 0. Therefore, MD is equals 0. So we are going to plot these remaining bending moments diagrams. And starting with bending moment at A, that is 0. Bending moment at B, that is 7. So that is 7. Let's gaze about that point. So let me remove this 12. I'm gonna write it later. So join this to A, which is 0 at that point. So let me return my 12 kilonewton meter. So here we have 37.8. 37.8 kNm. Then the bending moment at C, negative 20. So we are going to join this bending moment to that bending moment at C. Then bending moment at D definitely is 0. So this happens to be a positive bending moment, sorry. This one is a negative bending moment, positive bending moment, and negative bending moment. Then to complete our bending moment diagram, we are going to shade off its outline so that our bending moment diagram becomes very visible, and very clear. And that is how we plot the bending moment diagram for an overhanging beam. Now from there, we are going to calculate the reactions. Now, After plotting the bending moment diagram, the next thing we are going to do is to calculate the reactions, and in this case the reaction at A, at B, as well as at C. And we are going to begin with the span BC, and we are going to take moments about B. Remember, the sum of all the anti-clockwise moments must be equal to the sum of all the clockwise moments. So in this case, we are going to have the following anti-clockwise moments. RC multiplied by the distance from C to B, which is 6 meters. Therefore, that is RC times 6. Then we add an anti-clockwise moment, that is the bending moment at B, which we got as 37.8. This one will be equal to the following clockwise moments. 10 times the distance from D to B, which is 8 meters. So we got 10 times 8. And then we add, between C and B, we have a UDL of 10 kilonewtons per meter. Multiply by the span over which it is distributed, that is 6 meters. And then it is going to act at the mid of that span. So we divide the span by 2. This will give us RC times 6 plus 37.8 being equal to 80 plus, this is going to be 180. 80 plus 180. And we are going to have RC times 6 being equal to 80 plus 180, that is 260. So we got 260. Then we subtract this 37.8, so minus 37.8, which is going to give us 222.2. So we got 222.2. And to get the value of RC, we are going to divide both sides by 6. And when we do so, we are going to have the reaction at C being equal to 37.03 kilonewtons. So that is the reaction at the support C. Then from there, we are going to take moments, taking moments about B from the support A. And in this case, this is for the span A to B. Therefore, for the span AB, we take moments about B from A. And in this case, we are going to have the following. Clockwise moment, RA times the distance from A to B, which is 4. So that is RA times 4 plus the bending moment at B, which is 37.8 kilonewton meter, being equal to, between AB we have a UDL of 6 kilonewtons per meter, multiplied by the span over which it is distributed, times half of that span. So this is going to give us RA times 4 being equal to, this is going to be 48 minus 37.8. 37.8. And this is going to give us the following. RA will be equal to 48 minus 37.8, that is 10.2. So we got 10.2. Then we divide by 4, and that is going to give us a reaction at A being equal to 2.55 kilonewtons. So that is the reaction at the support A. From there, we go to reaction at we are remaining with the reaction at B, and for us to get the reaction at B, we are going to say this: the sum of all the upward acting forces must be equal to the sum of all the downward acting forces. So we are going to have RA plus RB plus RC. Those are the upward acting forces. which must be equal to downward acting forces. Between span AB, we have a UDL of 6 kilonewtons per meter. We multiply by the span over which it is distributed, that is converting it to point rod. Between the span B and C, we have a UDL of 10 times the span 6. And at the overhanging end D, we have a point rod of 10 kilonewtons. Now, the reaction at A is 2.55 kilonewtons. Reaction at B, we don't know. Reaction at C is 37.03. So 37.03. Being equal to 6 times 4, that is 24. 10 times 6, that is 60, plus 10. This is going to give us the following: 2.55 plus 37.03, that is 39.58. So we got 39.58 plus RB, which is going to be equal to 24 plus 70, that happens to be 94. So we got 94. And is going to give us the reaction at B, reaction of 94 minus 39.58. And that is going to be equal to reaction at B, 54.42. 54.42 kilonewtons. So that is the reaction at B. After getting the values of the reactions, we are going to write them on our loaded beam. Reaction at A, 2.55 kilonewtons. Reaction at B, 54.42 kilonewtons. And reaction at C, we got it as 37.03. 37.03. Then finally, ladies and gentlemen, we are going to calculate the shear forces, so that we use those shear force calculations to plot the shear force diagram. So shear force calculations. We are going to begin with the shear force between D and C, that is the overhanging end. And the shear force there is going to be negative 10 kilonewtons, negative since that end is overhanging. Then we go to shear force at C. And the shear force at C will be this negative 10 kilonewtons. We add the reaction at C, which is 37.03. Therefore, plus 37.03, which is going to give us 27.03 kilonewtons. Then from there we go to shear force between C and B. So the shear force between C and B is going to change uniformly from 27.03 to 27.03 minus, between C and B we have a UDL of 10 kilonewtons per meter. Convert it to point rod, that is multiplying it by the span over which it is distributed, that is 10 times 6. And this is going to give us a shear force of negative 32.97 kilonewtons. Then from there we go to shear force at B, at the support B. And the shear force at the support B will be the negative 32.97 kilonewtons plus the reaction at B, which is 54.42 kilonewtons. So we add 54.42 kilonewtons, which is going to give us a shear force of 21.45 kilonewtons. Then we go to shear force between B and A, which is going to change uniformly from 21.45 to 21.45 minus, between B and A we have a UDL of 6 kilonewtons per meter, and it is distributed over a span of 4 meters. So converting it to point rod, multiply the UDL times the span, which is 4. Therefore 6 times 4, that is 24. So 21.45 minus 24, which is going to give us negative 2.55 kilonewtons. And finally, the shear force at the shear force at A is going to be equivalent to shear force between B and A, which is negative 2.55 kilonewtons. And when you look at the shear force at A, you'll find that it is equivalent to the reaction at A. That, in most cases, is always the situation. So we now got all the shear forces. We can now use these shear force calculations to plot the shear force diagram. And we are going to begin with the shear force between D and C, which is negative 10. Negative 10, the negative shear forces will appear below this horizontal line. So approximate 10 to be at that point. So we are going to have a shear force diagram that is rectangular in form. So that is 10 kilonewtons. Shear force at C, that is 27.03, appearing above this horizontal line. So 27, say that point. So this is 27.03 kilonewtons. Then the shear force between C and B will change uniformly from 27.03 to negative 32.97. So negative 32.97, let's say is at this point. So we got 32.97 kilonewtons. A uniform change from 27.03. So we are going to join it like that. Then join to the horizontal line. Then the shear force at B, 21.45. So 21.45, let's say is that at that point, 21.45 kilonewtons. So that is the shear force at B. That is the shear force at B. Then the shear force between B and A will change uniformly from 21.45 to negative 2.55. So let's say negative 2.55 at that point. So we got 2.55 kilonewtons. So join this 21.45 to the 2.55 kilonewtons. Same case, shear force at A. So this is a negative shear force, positive shear force, negative shear force, positive shear force, negative shear force. And please, ladies and gentlemen, don't forget to give us comments, encouragement comments. Tell us what you think about this. And if you have any questions somewhere you haven't understood, please always feel free to ask any question that you feel you didn't understand. So that is the end of our today's lesson. We are going to meet again in yet another episode. So please stay tuned. Thank you very, very much.